Here's an interesting question for you. How do you measure the output impedance of an amplifier? It's an active circuit, so you can't just use an ohm meter. Well, it turns out it's easier than you might think. I'm Professor Fiore, and I'll explain it all to you right now. All right, let's talk about measuring the output impedance of an amplifier. Output impedance is one of three basic parameters that we use to describe how our amplifier, in gross terms, interacts with the circuits around it. In other words, the driving source and eventually its load, possibly other circuits, right? Other stages. The other two would be the input impedance and the voltage gain. Given those three things, we can make a nice model of our amplifier stage. In other words, we just treat it as a voltage-controlled voltage source. There's a Z in, there's a Z out, and there's a certain amount of gain, and that's all there is to it. Granted, there's lots of other things like frequency response, distortion, compliance, but for our basic analysis, that's all we need. So output impedance is a really useful thing to know. The issue is you cannot use an ohm meter. Ohm meters can only be used on passive circuits, and obviously our amplifier is an active powered circuit. An ohm meter works by sending out a little current into the circuit under test that creates a voltage. We can measure that voltage and relate it back to whatever the resistance is. And of course, those are specifically designed for DC measurements. Impedance is really an AC characteristic. So technically, it has both magnitude and phase. And we can investigate that. I'll explain in just a sec. But many times when we're talking about an amplifier, for a very wide range of frequencies, the input impedance can be assumed to be relatively constant and pretty much resistive. Toward the frequency extremes, we'll start to see magnitude changes and a little bit more in the way of phase shifts. But it's not uncommon to hear something like, well, the input impedance of this or the output impedance of this stage is so many ohms. Done, right? We don't talk about a magnitude and an angle. You certainly can make plots of this. I'll explain that in a sec. But what's the basic idea? I mean, how do we in fact do it? Well, we actually go back to the model of our stage. In other words, that of a voltage-controlled voltage source. We just look at a voltage source, its internal impedance, which is our Z out basically, and then the load. And we can establish through basic series circuit laws, sort of a voltage divider in reverse is how some people like to describe it. We can figure out what the Z out value is. So, without further ado, this is what I'm talking about. We have an unloaded, this is the ideal voltage, right? An unloaded voltage. This represents the voltage that the amplifier produces into an infinite load. It doesn't really have to be infinite. It just needs to be really, really big, okay, compared to whatever your Z out or R out happens to be. Then we have this R out or Z out, as the case may be, and we can treat this as the internal impedance of this source. That's what we do in our model. Now, given the load, this just comprises a very simple series loop. We've got a source and we've got two resistors. So, you probably have already looked at this and realized if that's 100 ohms and this is 100 ohms, V loaded, in other words, the drop across our load, has got to be half of whatever this source is. Half of it drops on this 100 ohm, half of it drops on this 100 ohm, right? It's a basic voltage divider rule. But to calculate out, if you know our load and you know V unloaded and V loaded, we can figure out what R out is. This is the technique. Basically, in a series loop, current's constant. So the current through R out has to equal the current through R load. Well, what is the current through R out? Well, it's the voltage across it divided by the resistance. The voltage across it would be the voltage on one side, V unloaded, minus the other side, V loaded, right? There that is, divided by the resistance, R out. And of course, the current through R load is whatever the voltage across it happens to be, which is V loaded, and then divided by R load, right? So here's your equation, right? Now we just take this and we solve it in terms of R out. Easy enough. R out is that differential voltage, V unloaded minus V loaded, times R load divided by V loaded. So you can go into lab, right, very easily determine V unloaded by just having an infinite load out here. Or more practically speaking, you can throw, like in this case, like a 1 meg, 10 meg ohm resistor in there, something like that. Measure the voltage across it with an oscilloscope. Then, that basically tells you what V unloaded is, because there's no load. Then you turn around and throw the load on, and you measure that voltage again. That's your V loaded. So you now have V unloaded, V loaded, and of course you know what your actual load resistor is. So we can now apply the formula, right? So I would throw in, let's say I throw in a volt over here. Okay, I have a 1 meg ohm resistor out here. I measure V loaded. That should be the 1 volt that I set up initially. Because this is a meg, this is 100 ohms, let's say, right? So there's going to be very, very little loss out here. I'm going to see pretty much the whole thing. If it makes you happier, think of it as, 0.999 something, right? But that's going to be your V unloaded in this equation. Now, you rip out that 10 meg ohm resistor, 1 meg ohm resistor, whatever it was. You put in this load, 100 ohm resistor, and you measure your V loaded again with your scope. Subtract, multiply by this quantity, R load over V loaded, and bingo, you got your R load. It's that simple. Really, it really is just sort of like a voltage divider backwards kind of thing, because you're comparing this voltage and this voltage against those two resistances. It really all comes into this, okay? So this is sort of a practical way of doing it with a scope, because you're going to measure the V unloaded in the first step, then you're going to measure the V loaded in the second step, and you can just, like I said, get your calculator, boom, 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 you're done. Now, word of caution, if you're going to do this across frequency range, you're probably not going to use a standard cheapy DMM, because a lot of times those things are limited in frequency. If you're lucky, it'll go up to a kilohertz. You put in a 10 kilohertz sine wave, who knows what you're going to get. I've seen some meters, they don't do well over, about 100 hertz. So, all depends on what you spend. Now, you can spend money and get some really nice meters. We have some really nice meters in our lab that go up to either 50 or 50 kilohertz or 100 kilohertz, I forget what. Those are our true RMS reading multimeters, but of course, they were hundreds of dollars a pop. A scope, however, doesn't have that kind of limitation. A scope has a really, really wide bandwidth. So the only difference there is, instead of, reading a value conveniently in digital form, an RMS voltage, you're going to have to read it as a peak value. Well, no big deal. Whether it's peak or peak to peak, however you want to do it, you can do it, right? The other nice thing about using a scope is you can, if you're doing a wide-ranging plot on this, you can also see what the phase shift is, right? So that can be handy. The math is, a little bit more involved, obviously. I'm going to look at this strictly as a, sort of middle of the spectrum kind of thing, where everything is assumed to be resistive. All right, so let's go and look at a little amplifier. So here's a little Class B amplifier. There's one other thing I should indicate here, and that is these calculations assume that you're getting relatively low distortion in your two voltages. If you have a lot of distortion, that's going to throw off the accuracy. Right? So first thing I'm going to do here, notice I have a really big resistance out here. I have a 1 meg ohm resistor. This is my open case. I'm doing it this way instead of just ripping out the resistor, because it's really easy to do in the sim. I can just double click on this and change the resistor value. In lab, like I said, you might just rip out the resistor, right? Reconnect it, off you go. In this case, I just have the one resistor. I'm going to leave it connected. I'm just going to change the value to, like I said, a ridiculously high value. Anyway, so here's a meg. I've got a 1 volt peak, 1 kilohertz sine wave coming in. And what I'm going to do is I'm just going to run a transient analysis just to check. Okay, now I'm starting this at 1 second, and I'm going to go to 1.002 seconds. You might say, why are you doing that? Well, the reason I'm doing that is because it's going to take a little while for these rather large capacitors to charge up. And I don't want to see a little DC offset creeping into my output while that's happening. But in any case, here is my signal. Okay, so this is my output. You can see it's just about 1 volt, right? This should be exactly 1 volt, but it's, not quite. Because again, there is a finite output impedance here. I'm getting like 993, whatever the heck it works out to. Okay, so that looks good. Right? I'm not in any way upset by that. It looks like a nice sine wave, but your eye isn't really, really great at looking at distortion. So we'll do a little Fourier on here. And oh, look at that. We get 0.0015, basically 0.0015% THD. That's like super hi-fi. Okay, so I'm not at all concerned about that. Great. All right, now let's go take our load and bring that down to a reasonable value here. I'm going to use 100 ohms. If I go really low, like if I try to put an 8 ohm load on here, this guy's going to start clipping and we're going to get a lot of distortion. I mean, this is only an 04 and an 06. I use these a lot because they're very common and it's something you can, breadboard on your own. Don't put a really big signal in though, because you could have a little bit too much power dissipation and you might fry these if you're not careful. So this will be fine though, 1 volt, and then, my, what did I say there, 100 ohm load. This will be fine. Okay. So this is my loaded case. All right. This is my loaded case. Let's go check this. All right. You can see that pop down just a little bit. All right. Boom. Just a little bit in amplitude. Still looks pretty nice. Now we could come in here and just check that amplitude. And we had like, 0.999 something. Now we're getting like 0.943, somewhere around there. All right, that's my peak value. So that little bit indicates, yeah, the internal impedance, the Z out here, is where we're losing a little bit of that signal. Now, sometimes in a power amplifier, what they'll have you do, well, in a general case, usually not with a power amplifier, I should retract that, is they'll do a matched impedance thing. They'll put a potentiometer out here or resistance decade box, and they have you adjust this until your V load falls to half of your unloaded. And when that happens, you have the matched resistance case, which is what I showed you initially, right, with the 200s. So when that happens, you know that whatever your load is, that's your Z out. That's not really a good idea with a power amplifier, because the power amplifier impedances are usually a lot smaller than what your load is. And you can get some really nasty distortion, clipping, overheating, maybe transistors go bye-bye on you. So this way, the way I'm doing it here, it's a little tiny bit more calculation, but it's safe. Let's look at it that way. Okay, so also we need to look at the distortion on that, because again, we want to make sure it's relatively low. All right, so this has gone up because the load is obviously demanding a lot more current, right? 100 ohms instead of 1 megohm. We're up to 0.34%. So not exactly hi-fi, but certainly good enough for our approximations on this, right? That'll be great. Okay, so to get some accuracy here, what I'm going to do is I'm just going to grab the AC analysis because I want to point out a couple of other things. So, all right, this is just going to tell me it's 668.7418 millivolts. Let me click on here, and we can see some other things here, right? So, it's saying it's 900 and whatever millivolts, but the bottom is one I want to look at. And this might be hard to see depending on what you're using to watch this video, but this is about 1/3 of a degree as far as phase shift is concerned. So it's inconsequential. All right. Now let's go back to that open circuit case where I'm using the 1 meg in my simulator. And I'll do the same thing. All right, so now we're up to 703.5 basically millivolts instead of the 600 and whatever we had. The phase is not even 0.2 of a degree. So again, nicely resistive, right? This is working out really well for us. So I've written these down, and here's our results, okay? With the open circuit case, actually 1 meg, we got 703 and change millivolts. The distortion was vanishingly small, 0.0015%. The R load being 100 ohms, we got a smaller potential, 668.7. THD is a bit larger, but still not terrible, 0.34%. So now I can take these two numbers and stuff them into my equation, right? This is the equation we derived. So you take your 703, subtract your 668, get that differential voltage. That's basically the voltage dropped across the internal Z out, and then multiply by your Z load and V load combo, and bloop, that works out to 5.2 ohms. There you go. Done. All right. So of course we can calculate what that is, theoretically, and we talk about this in the textbook, right? In the semiconductor textbook. Just another plug. Remember, it's free. You can get it in either PDF or Open Document Text (ODT) format. Just go to my websites. The links are out there, so you can just download that. This is in the section on the Class A and Class B power amplifiers. But this is how you would do it in lab, right? You would get out your scope, typically, unless you happen to have a wide band AC RMS reading millivolt meter. You might have one kicking around, but if all you have is an inexpensive little DMM, and then, like I said, it dies at a few hundred hertz, maybe 1 kilohertz, you're not going to be able to do a check for your input impedance at 10 kilohertz or something like that. But a scope, absolutely no problem. And even though I did use RMS for my computations over here, you don't have to. You can use peak, you can use peak to peak. Just make sure you use the same for each, right? The loaded and the unloaded, you just have to make sure that they're the same, right? RMS, peak, peak to peak. Okay? So you don't have that limitation with the scope. You don't have a frequency limitation, so that will work really well. Now, if you want to, you could do this at a whole bunch of frequencies, right? You got an audio amplifier and you say, hey, what is it, 100 hertz? So I'll throw in 100 hertz back here. 1 kilohertz, 10 kilohertz, 20 kilohertz, whatever. I can get all of those, put them on a, piece of graph paper, right? Plot them, and I can see what my impedance is actually doing. You can have the magnitude of it, and you can also have the phase of it. Pretty cool, right? All right. Well, I hope you've learned something from this. I hope you enjoyed it. This is Professor Fiore saying, until next time, take care and have a good one.